All right, let's dive into one of the most powerful problem-solving techniques out there, dynamic programming. Now, I know the name sounds kind of heavy, but I promise it's an incredibly intuitive way to solve problems that seem, well, pretty much impossible. Let's kick things off with one of those problems right now.
So picture this. You've got two ridiculously long strings of text. Think two strands of DNA, each with millions, maybe billions of characters. And your job is to find the longest sequence of characters that shows up in both of those strings, in the exact same order. I mean, where would you even start? This isn't just some brain teaser, by the way. It's a very real problem in computational biology.
Well, you could always try the brute force way, right? You could literally list out every single possible subsequence from the first DNA strand, and then check if it exists in the second one. The catch? For a string of length m, there are 2 to the power of m subsequences. That number gets mind-bogglingly huge, incredibly fast. So that approach isn't just slow, it's fundamentally broken. There's gotta be a smarter way. And that smarter way, you guessed it, is dynamic programming. The core idea is just brilliantly simple. Instead of trying to solve the massive problem all at once, you break it way down, you solve the tiniest, easiest pieces first, and then you use those answers to build up to the final solution. But you can't use this trick on just any problem. For this whole build-it-up strategy to work, a problem needs to have 2 very special characteristics. So what are they? First up, it needs something called optimal substructure. All this really means is that the best solution to the big problem is made up of the best solutions to its smaller parts. So for our DNA problem, it means the longest common sequence of 2 long strings has to contain the longest common sequence of shorter versions of those same strings. It's a simple idea, but it's absolutely crucial. The second property is overlapping subproblems. This is what happens when you start breaking down the main problem and you notice, hey, wait a minute, I'm solving the exact same little subproblem over and over and over again. Now, doing the same work repeatedly is obviously super inefficient, but it's also a huge clue that we can make things way faster. And this is where the magic really kicks in. We take advantage of those overlapping subproblems. The whole strategy is this: solve each little piece just one time, save the answer somewhere, and then anytime you need that answer again, you just look it up instead of redoing all the work. You know, for anyone who's worked with relational databases, this should sound really familiar. It's basically like building a lookup table or creating a materialized view. You do all the heavy lifting up front to pre-calculate the results, so that every time you need to query for the answer to a subproblem later on, it's instant. Okay, let's make this real. We're going to walk through finding the longest common subsequence, or LCS, for 2 strings. And the main tool we're going to use is a simple grid. This is where we'll build our solution one little piece at a time. So here's our grid. Think of the columns as representing our first string and the rows representing our second. Every single cell in this grid is going to hold the answer to a tiny subproblem. What's the LCS length for this little piece of the strings? And we always start with the easiest cases, comparing a string to an empty string. The longest common sequence there is, of course, 0. That's why that first row and first column are all filled with zeros. Now, to fill in the rest of the table, we just follow 2 incredibly simple rules, over and over. If the characters for the current row and column match, great. The value for our cell is just 1 plus the value from the diagonal cell up and to the left. If they don't match, no problem. We just take the bigger value from either the cell directly above us or the cell directly to the left. That's it. It's just a simple, repeatable process. And check it out. This is the real power of the bottom-up approach. We started with the absolute smallest problems in that top left corner, and we worked our way down, cell by cell. Each new cell we filled used the answers from its neighbors that we had already solved. We just methodically fill the whole grid until, bam, we land on that final cell in the bottom right corner. And that one number, right there in that final cell, that's our answer. That is the length of the longest common subsequence for the 2 entire strings. We solved this huge, messy problem just by systematically building on the answers to all the tiny ones. Now, what's really cool is that this table building method is super versatile. It's not a one-trick pony for finding common stuff. We can adapt the exact same strategy to solve other complex problems, like figuring out the cheapest way to transform one string into another. So imagine you want to change string X into string Y. You're only allowed to do 4 things. You can copy a character if it's the same, You can replace a character, you can delete one, or you can insert one. And each of those actions has a cost. The goal is to find the series of steps that has the lowest total cost.
So how in the world do we find that cheapest possible transformation path? If you're thinking, I bet we could build a table for that, then you are absolutely right. It's the exact same grid approach, only this time each cell stores the minimum cost to transform one part of a string into another. To fill a cell, we just look at its neighbors and figure out the cheapest next move. If the characters match, we can just copy, and we inherit the cost from the diagonal cell. If they don't match, we check our options. What's the cost to replace, to delete, to insert? We just pick the cheapest of those options at every single step, and that simple logic builds out the entire solution for us, from the bottom up.
So what's the big idea here? What's the main lesson behind dynamic programming? It really all comes down to the incredible power of solving things incrementally. I mean, what this method really does is pretty incredible. It takes problems that are functionally impossible, the kind that would take a brute force computer longer than the age of the universe to figure out, and it turns them into something totally manageable. It's the difference between impossible and efficient. So to recap, the playbook is pretty much always the same. First, you check if your problem has that optimal substructure and those overlapping subproblems. If it does, you're in business. Then you figure out how to build a table of solutions, starting from the simplest cases you can think of. And then you just fill out the table, using your stored results to solve slightly bigger problems until you get to the very end. But at the end of the day, this is so much more than just a programming trick. It's a mental model. It's a whole strategy for taking apart any huge, complex challenge. Find the basic building blocks, solve each one of them once, and then build your way to a complete solution without ever wasting your effort. So I'll just leave you with this question. What's a big, messy, seemingly impossible problem in your world that you could start making real progress on? Not by trying to solve the whole thing at once, but just by figuring out and solving the smallest, simplest piece first. And that's it for this explainer. If you found this helpful for getting your head around a complex topic, do me a favor and hit that like button, share it with a friend, and subscribe for more deep dives into big ideas. Thanks for watching.